This video was brought to you by GeneralPAC.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/GeneralPAC. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies. Electric Machines Part 2B Section 2, Induction Motors, Slip and Equivalent Circuit. This is Part 2B Section 2 of Topic 2 in the series of electric machines, and in this part we will be discussing the induction motor slip and equivalent circuit. Now we started this series with the introduction to AC machines, which led us to induction motors, and in Part 2B Section 1, in the previous part, we talked about the construction and working principles of the induction motors, and in this part we will be talking about the concept of slips and introduce you to the equivalent circuit of induction motors. We have a long way to go for this topic, so let's get started. So first we'll start with slip. As discussed earlier, an induction motor has a rotating magnetic field which rotates at the speed known as synchronous speed, or n-sync. The rotor, however, rotates at a speed slightly less than the synchronous speed, and the difference in the synchronous speed and the rotor speed is known as slip speed. So n-slip is equal to n-sync minus n-rotor. Another way of representing the slip speed is by comparing it to the synchronous speed in functional form, i.e. the slip speed is divided by the synchronous speed. Now the quantity is known as the slip only, and it is a good numerical indicator of the difference between slip speed and synchronous speed. So the slip is equal to n-slip divided by n-sync times 100. And the equation can also be written as slip is equal to n-sync minus the n-rotor divided by the n-sync times 100. Now let's see a solved example in Electric Machinery Fundamentals by Chapman, example 7-1. Consider a 4-pole 60 Hz motor with the speed of 1,710 RPM, that's n-rotor. What will be the value of slip for this motor? As we know, the formula for the slip of the motor is equal to n-sync minus n-rotor divided by n-sync times 100. First, we will find out the value of synchronous speed. Then by putting it above the formula, we will get the value of slip. So for synchronous speed is given by 120 times of electric frequency divided by the number of poles of the motor. So n-sync again is equal to 120 times F, which is the frequency, divided by P, which is the number of poles. As the given frequency is 60 Hz and the number of poles are 4, so by putting these values in the formula of n-sync, we will get the magnitude of a synchronous speed of 1800 RPM. Again, is n-sync is equal to 120 times 60 divided by 4, which gives us 1800 RPM. Now putting this value of n-sync and also given the value of the rotor speed, the slip is simply equals to 1800 minus 1710 divided by 1800 times 100. Moving on, there's another term that is used frequently in induction motor, and that is the rotor frequency, which is the product of electrical supply frequency at stator Fs and slip S. So Fr, which is the rotor frequency, that is equal to S times Fs. You may ask why the rotor speed is always less than the synchronous speed. This is because same values of synchronous speed and rotor speed will result in zero relative speed. This means that there is no EMF induced in the rotor, and therefore no rotor current exists. So the rotor slows down. Upon slowing down, rotor current is induced again, and the relative speed is attained again, causing the rotor to rotate again smoothly. Returning back, the equivalent circuit of an induction motor is similar to that of a transformer. due to the fact that both machines use the same phenomena of induction, that is, the changing magnetic field created by primary winding induced voltage in secondary winding. This is conceptually similar to the induction of the voltage in the rotor through the stator winding, and the only difference being that the ratio of the primary and secondary side is always 1. So we can say that the transformer primary winding is similar to the stator, and the transformer secondary winding is similar to the rotor. Looking at the per phase equivalent circuit of the induction motor, as current flows through the stator and the rotor windings, heating effects through resistive losses in the motor winding, and self-induction in iron core exists in stator. In the figure of the equivalent circuit for the induction motor, this resistance is taken as R1 and the induction reactance is taken as X1 in series. Meanwhile, in the rotor, resistance is RR and the reactance is XR in series. Now, the core resistance RC corresponds to the resistive core losses, and induction reactance XM corresponds to the mutual field between the stator and the rotor. RC and XM are placed in parallel. Next, we have AEFF, or the effective turns ratio. This is the ratio between per phase number of turns of stator winding to that of the rotor windings per phase. Now, if the rotor speeds up, the slip changes from 1 to some lesser value, and the change of speed in the rotor changes the impedance of the rotor circuit, which is expressed in the equivalent rotor circuit as the rotor resistance RR divided by slip. As shown in the figure, the total rotor impedance can be series summed as RR divided by X plus J times XR0. Now, for the final equivalent circuit, all we have to do is to refer or shift the rotor circuit to the stator side and eliminate the AEFF air gap between the stator and the rotor, as we do in the transformer analysis, i.e. refer secondary circuit to the primary circuit, or refer the secondary winding to the primary winding, and vice versa. Now, this can be done by first multiplying the effective turns ratio, or the AEFF, with the rotor voltage ER0. This product can be denoted as ER. Hence, ER is equal to AEFF times ER0. And ER will be represented in the final equivalent circuit as E1. I know it's a little bit confusing, but we really need to keep track of all of our variables like this. Now, the second thing is multiplying the square of AEFF with the rotor impedance. To refer it, we can express the obtained result as Z2. So Z2 is equal to AEFF squared times RR divided by S plus JXR0, or Z2 is equal to AEFF squared times RR divided by S plus JAEFF squared times XR0. Now, I know this can be a little bit confusing, but we're getting to the very end of the equivalent circuit, so hang in there for me. We will model the series sum of the rotor impedance, i.e. Z2, in the final equivalent circuit by simply as R2 divided by S and JX2, which represent the referred value of the rotor resistance and reactance. And this may be directly measured or calculated from RR and XR0 if AEFF is known. And finally, dividing the rotor current IR by effective turns ratio AEFF. I2 is the final equivalent circuit, can be expressed as I2 is equal to IR divided by AEFF. So now, after all of that, we finally get to the equivalent circuit. And here is the final equivalent circuit for the induction motor, which is modeled after referring the rotor side to the stator side, right? Just like how we do for a transformer. So this equivalent circuit looks very, very similar to that of a transformer, except for the parameters are different and they are for the induction motor.
We hope that you support us by becoming our patron and subscribing through patreon.com/GeneralPAC. Your generous subscription will help us continue make high quality power system video tutorials. Thank you.